Hello, everybody. Mr. Danahauer here, coming to you today to talk about Newton's laws of motion. Let's see here. Mr. Isaac Newton was a very well studied mathematician. He was born in around the 1642, and was really described many ways. He was a mathematician, physicist. He was also into astronomy, alchemy, and a lot of other topics as a scientist. But by the time he was 23, he had already really developed his laws of motion. And that might seem weird to us, some of these laws, because they seem somewhat elementary or simple to understand. But a lot of scientists of his time, physicists, really didn't have a solid understanding of things like friction, and inertia, and some other principles of motion, these laws that he developed. So they were quite foundational. They're now foundational for physics and everything that happens, really. um, he also defined laws towards related to gravity, such as the universal law of gravitation, and a lot of that applies to his studies as an astronomer. He also built the first reflecting, or one of the first reflecting telescopes that was used to study the universe. He wrote his most famous publication or book was about math. He was really a mathematician. He also did a lot of work with optics. And he also is credited with partially inventing calculus. And from what I remember, he actually did some of this during the Great Plague when he went off to college. This was all in London. When he went off to college, he uh, f- he earned his bachelor's degree, and then when he was going to continue for his master's degree. The school was shut down because of the plague. They were worried, much like we've kind of shut things down a little bit during the COVID pandemic. And during that time, he continued to work and study and invent. He didn't really sit back and watch Netflix. He really kept working on all of these ideas that are foundational for physics nowadays. Uh, a- and he was also one of the first scientists that showed that light is composed of the colors of the rainbow, which we've been also talking about in our energy unit here. Um, and he, like I said, he developed a reflecting telescope. So we're going to take a little bit of time here to talk about his three laws. But in order to understand those laws, we need to define what a force is, because all of Newton's laws of motion have to do with forces. And so there are three parts to define a force. First of all, the first of the three parts is that a force is always a push or a pull. And so you can see from my diagrams, the shot putter there is about to throw the shot, and that force that she's going to put on that ball is a push, right? That's a force. Likewise, the guys that are pulling on the tug of war rope there, they are applying a force by pulling. And so, first part is a force is a push or a pull. That would be a great thing to write down. The second part of a force is that it's always acting on an object. So typically, we can't really define a force if it's not acting on something. In order for there to be a push or a pull, there has to be an object that's being pushed or pulled on. And even if there's not a direct contact between those things, if you think about gravitational force between, let's say, the Earth and the Moon, why is the Moon constantly orbiting the Earth? Because of the Earth's gravitational pull on the Moon. There's still a force there. The force of the gravity from the Earth is acting on the moon, and the moon's actually acting on the Earth, which influences our tides. So if you've ever been to the ocean and seen the tides go up and down, high and low throughout the day, that's because of the moon's pull on the Earth. And the last part is to understand about forces is these are vector quantities. And we've looked at another vector quantity already whenever we talked about bonds. And if you look at a dipole and a bond, we always labeled the dipole in the direction of the pull of the electrons, the element that had the higher electronegativity. And then we also could draw it a different size depending on the difference, or the magnitude of the pull based on electronegativity values. So, lots of whenever we define forces and talk about force diagrams, especially in physics, we typically draw vectors to show those forces, and we can draw them the direction of the force, And then we also can draw them different sizes. The arrow can be different sizes depending on the magnitude or how strong that particular force is. So those are the three parts of a force. And now we'll get into Newton's three laws. So his first, we'll go through each one of these and define it, both the short and long definition. As always, as you're taking notes, please make your notes work for you. Um, Sometimes when we just copy everything down from a slide, it's harder for us to connect with that information. So read it and then write it down that makes sense. And then also as we go through, I'm going to try to provide you some examples. After we've gone through all the laws, I'll go through some more examples together. So the first law of motion is inertia. So the short name is Newton's first law of motion is often said to be inertia. And the full definition or description is sort of long, right? Objects in motion stay in motion, and objects at rest stay at rest unless they're acted on by an unbalanced force. If you need to pause the video for a second to write that down, go ahead. So, a couple of important things about inertia, as I describe this a little bit. If you think about an object sitting on a table, there is no way for that object, let's say a mouse. Okay, we've got a mouse. I'm looking at my mouse sitting here at my computer, and that mouse is not going to move. Okay, it's going to continue to do what it's doing unless it's acted on by an unbalanced force, meaning I push that mouse forward or pull it backwards. We might say, well, why is the mouse not going in one direction or another, up or down? Because there is not an unbalanced force. The force of gravity is pulling it down, and the force, which we call the normal force from the table, is pushing it back up. And those two forces are balanced, and so the mouse is not going to move in any direction. Now, if we add some speed to something, right? Let's take a ball, okay, and we're going to roll that ball across the floor. Does that ball go on does it continue to go on and never stop? And the answer, of course, is no, right? It stops. Why does that ball stop after a while? So we go out in the hallway, we roll it, and it makes it partway down the hall and it slows down and eventually stops. Why is that? Because we have the force of friction and a tiny bit of air resistance. Those are forces, and they are pushing against the ball, resisting its motion. So slowly that is changing what the ball is doing, right? Now, it's important to understand. Another way to think about this is it's the tendency of an object to resist changing velocity. So, velocity is just speed that has direction. We'll talk some more about that in the future. But if we have an object that is going in a certain direction, let's say a car, okay, that car is moving, and it's going to take a certain amount of force to change what it's doing. And that's what inertia is. The harder it is to change what it's doing, the more inertia something has. So let's take that car. We got a little sports car, and then we have a big school bus, right? Let's compare those two. Which one has more inertia? Well, it's much harder to get the school bus going because it has more mass. And so it also has more inertia. The sports car, on the other hand, can get going. If you're at a stoplight, can get going pretty quickly, right? We can accelerate very fast in that sports car because it has less mass, and that also means that it has a smaller inertia. It has less inertia than the school bus. I would recommend that you jot down this statement. It's not on the slides here, but inertia, the amount of inertia is dependent on the mass of the object. It is not dependent on the velocity or how fast the object is going. So to make more sense to you, if I have a school bus again that's sitting at a stoplight, and then that school bus starts going down the road and is moving 50 miles an hour, does it have a different amount of inertia when it's stopped versus when it's moving 50 miles an hour? And the answer is no, because the mass is the same. Whether it's stopped or moving, it's going to take the same amount of force to change what that school bus is doing. So let me say that one more time. Inertia is dependent on mass, not velocity. Okay. Okay. So that's Newton's first law. A couple of examples, I've kind of already given you a couple, but let me give you another one. It's very common. Why do we wear seatbelts in cars? Why is that a law, right? To protect people, but why do we care? Well, if you think about it, if you are going, let's say, you're sitting in the front seat of your car and you're heading to, I don't know, Wendy's to get a frosty, right? And you're cruising down Harmony Road, and you all of a sudden it's a red light coming up, and you have to hit the brakes, right? Your body is traveling as fast as your car is. If you're going 55 miles an hour, you and everything inside the car are going 55 miles an hour. So, for that reason, when you hit the brakes, the car has a way to slow down and stop, but your body does not. It will continue to go in the direction it's going at the same speed unless something stops your body from moving. And that's the purpose of a seatbelt, right? If, for example, instead of stopping at the stoplight, you accidentally rear-ended somebody, and you stop very quickly, what we would call have a rapid deceleration. Instead of, if you don't have your seatbelt on, where are you going? Your body's going to keep going and potentially go through the windshield. If you have your seatbelt on, all of that force from the seatbelt holding you back is going to stop you from moving and hitting the windshield. So, uh, PSA, wear your seatbelt, right? They're important because of inertia. That's why we wear seatbelts. And that's not just for stopping and going. If you think about turning, okay, let's say you're in a Jeep and there's no side doors. It's really nice outside. So you got the top down, you got the side doors off, and your friend who's driving takes a really sharp left turn. Your body is going to want to keep going in the straight. If you don't have your seatbelt on, your body's going to want to keep going straight. But the Jeep is turning out from underneath you. So what might happen if you don't have your seatbelt on? You fall out the side. Okay. And if you have your seatbelt on, the seatbelt's going to keep you from going straight, and it's going to sort of push you in the same direction the car is going. So a couple of examples there for inertia, and we'll see a few more in the video in just a little bit, and also some examples in the stations lab you're going to do. Second law. The second law is often written as and said as an equation. F equals ma is the short name. It's an equation, and that is force is equal. The force on an object is equal to the mass of the object times the acceleration of an object. Another way to say this is that the acceleration on an object is directly proportional to the force acting on the object. And I would have you add that it's inversely proportional to the mass of the object. So the acceleration on an object is directly proportional to the force and inversely proportional to the mass of the object. So let's talk about the variables here. If this is an equation just like the density equation or the wave speed equation that we've used, and you can plug in known variables, which we will do for this equation. And let's say we're given a mass and an acceleration of an object, we can determine the force. And so what are those variables? Let's write those down really quick. The three variables are first the force applied, and in honor of Sir Isaac Newton and his laws, um, the unit that we use for force is the Newton, capital N. Mass is, of course, the mass of the object. Now, keep in mind, this is not weight. Mass and weight are different. Mass is going to be measured in kilograms for our equation. And acceleration we haven't really talked much about acceleration, but acceleration is how quickly the speed of an object changes or how quickly the velocity changes. And so I would say if you start at rest and you speed up really quickly in that sports car, of course, you all know that's a very fast acceleration because your speed is changing rapidly. Whereas if you're in that school bus and the school bus driver floors it, yeah, acceleration's going to be a little slower, right? So we're not going to change velocity as quickly in that scenario. So acceleration, we'll talk more about acceleration later, but that's one of the variables here. So let's talk, what does this mean about directly and inversely proportional? If we think about acceleration in that scenario that I just gave you, okay, let's just say that the force applied uh, by both the sports car and the school bus, their engines and their wheels, they apply the same amount of force, pushing the car and the school bus forward, the same amount of force. But which one's going to accelerate more? The object that has less mass is going to accelerate more. That's what this equation is saying. So the acceleration of the object is inversely proportional to the mass. The bigger the mass, the lower the acceleration is going to be. But the acceleration is directly proportional to the force. So let's say I have, let's see, a box. Okay, it's a heavy box in the garage, and I need to push it across the floor. All right. If I push it by myself and it's pretty heavy, it's going to move very slowly. The acceleration is going to be small. But if I get my family to come help me push the box and all four of us are pushing on that box, now we have a much greater force. And so the box is going to accelerate much more quickly because force and acceleration are directly proportional. So simply put, the harder I push on something or pull on something, the faster it's going to move, right? And inverse to that, the heavier an object is, if the force is the same, the heavier it is, the less it's going to accelerate. Okay. So we'll look at some examples of that throughout our lesson today as well. So let's look at the third law. This is action reaction. Okay, that's the short name. And the description is pretty simple. For every action, there's an equal and opposite reaction. So we should jot that down real quick. This students have a hard time understanding this a lot of times. It's seems like a very simple law, but when you start to think about, well, what are the opposing forces, it can actually get a little bit tricky sometimes. So here's the thing: forces always come in pairs, and neither force would exist without the other force. Okay. So for example, if how are we able to walk, right? We're moving forward, we're accelerating when we walk or run, so we know that there must be a force, an uneven force, a force pushing in one direction, and that's forces coming from our feet, right? So when my foot pushes against the ground, because my muscles are like pushing my foot forward, as my foot pushes against the ground is pushing back on my foot. That's the pair of forces. The action is my foot pushing, and the reaction is the ground pushing back on that. Okay. So a lot of examples of that, and we'll see some in our next slideshow here. All right, now if we look at some examples here, the first one, this is commonly what I'll ask you. I'll give you a scenario and I'll say, which one of Newton's laws is this really referring to? And so if we look at any of the ones on this slide, we see the vectors, those arrows pointing in the direction of the force and the magnitude. And we can see, like for this car, right, the tire is applying a force on the ground in this direction, and the opposite force on that is the ground pushing the tire forward in this direction. So all of these scenarios really show that equal and opposite force. And which law is that? Newton's third law, action and reaction. Okay, likewise, here we've got the force of the guy pushing on the refrigerator, and that force him pushing, and there's an equal force pushing backward. Now, if you think about it, he could continue to push on this refrigerator as long as it's not moving. He's going to push on it, and it will continue to push back harder and harder until it gets moving, and then it's still pushing back on him, but the net force is being applied in this direction. And there's a lot more physics behind this. I'm simplifying things just to not overcomplicate stuff on our first go around here. So this is Newton's third law, a bunch of good examples of that. Here we go. What's this one example of? Now, I do want to say that in any scenario, we can apply all three laws. All three laws apply to every situation, but certain situations lend themselves really well to one of the three laws in particular. And so for this example, we have our zombie maybe pushing his bus, um and this is we could calculate, the question mark is on newtons here, which is the measurement or the unit we use for force. And so we could actually use Newton's second law here. The force is equal to the mass times the acceleration. We have the mass of the vehicle, 2,000 kilograms, and we have the acceleration, 0.05 meters per second squared, per second, and we can multiply those together. Force is equal to to mass times acceleration. And when we do that, we plug those numbers in, we get 100 newtons would be the a force being applied if it was moving at zero point zero 0.05 meters per second. So this is a great example of using Newton's second law to determine something. What about this one? You've got a guy maybe cruising along on the bike, not paying attention, and he's about to run these girls over, and he hits the brakes really hard and flies over the handlebars. Well, why is that? We talked about seatbelts. In this case, right, he applies the let's just say he's going 15 miles an hour on his bike. That's pretty fast through the grass, but whatever. And he hits those brake, right? The bike stops, but if he's not pushing on the bike or attached to the bike, inertia says that he's going to continue moving forward until something stops him. And so in this case, he actually continues to move forward, and he's holding onto his handlebars, so he's flipping over. So this is a really good example of Newton's first law of inertia. Another, application of this, like I said in the last one, is that you can apply all laws here. We could say, well, he's probably quite a bit more massive, like, heavier than the bike. And maybe the bike weighs 20 or 30 pounds, and, maybe he weighs 175 pounds. So he has a lot more inertia when he's going at the same speed of the bike, and it's going to take more force to slow him down and less force to slow the bike down. So again, we can apply all the laws here, but inertia is probably the best one reflected in this one. Here's another one. We have a force being applied by these sled dogs of 200 newtons and a mass of a rock of 50 kilograms. What's the acceleration on this sled with the rock in it? What's it going to be? Maybe that's not a rock. I don't know why they'd be pulling a big rock. Maybe this is a bag of supplies. So anyway, what would it be? Force equals mass times acceleration. If we rearrange the equation, we would have force divided by mass is equal to acceleration. So we could do 200 divided by 50 and get the acceleration of the cart here. Okay, so this is a good application of Newton's second law again. Here we go. So, how do rockets fly in space, right? A lot of people think that rockets move because they're pushing against something. And that's actually not really true. I mean, they are, but they're not pushing against the Earth. They're not pushing in space. There is nothing to push against. So, how is the space shuttle moving and adjusting? And the answer is Newton's third law, action reaction. So in essence, the rocket is throwing hot gases out the back, and the more massive they are and the more velocity the gases are being pushed with, the more force is being put on the rocket. And so the rocket is pushing out the gas, and the gas is pushing back on the rocket, which is what propels it forward. Sorry, I didn't say. So, which law is that? Newton's third law, action reaction. And we already looked at this one, right? Pushing yourself against the ground. So you're pushing on the ground, really the grass, but the ground is what you're pushing against, and the ground is pushing back on you. So again, third law there. The last one, this is a really good example. There's a whole bunch of ways we could describe the laws. And when you get into the stations today, you're going to find yourself in this situation where you're like, well, there's several laws that apply. And that's true. You just need to be able to describe how that law applies. So what could we say here? Well, first we could talk about Newton's first law of inertia, right? Why can't the boys, let's say they have about the same amount of strength here, and they're both pulling on these rocks. The big rock is not moving, and the small rock is. Why is that? Well, that big rock has a lot more inertia than the small rock. So it's going to require a lot more force to move it compared to the small rock. The big rock is going to resist changing what it's doing more than the small rock. Okay. So that's Newton's law of inertia we could apply there. The second law we could apply, because we could say, well, the acceleration on an object is inversely proportional to the mass, meaning the more massive something is, the harder it is to move, accelerate. It's not going to accelerate as much. So when we, plug in the mass of the rock, and the force applied by the buoy, we see the acceleration is either zero or much smaller, depending on how hard he's pulling. Whereas the little rock there has a smaller mass, and so it's going to require a small force, and it's going to accelerate or move more. Right. So, and then we could also apply action reaction here, because they're both pulling on the rope, and the rope's pulling back on them to a certain amount. We talked about cars and hitting things. This is another example of inertia, right? Tug of war, action reaction. And here's another one. This is a great example of inertia. Also, the second law, F equals ma. So we have a really big sumo wrestler and a little kid sumo wrestler. And the big sumo wrestler is going to have a lot of inertia, and the little sumo wrestler is going to not have very much inertia. So it's going to be very hard for the little guy to change what the big guy's doing, right? And that's why, whenever we have like wrestling competitions, mixed martial arts and stuff, they usually have weight classes to divide things up evenly. That's mainly because of things like inertia and Newton's second law. So, all right, those are some really good examples for you guys. Hopefully, you just jotted a couple of those down, and then you'll actually get to see some more examples here in just a minute.